Welcome to the Explainer. I'm your host from Forge College, and today we're diving straight into guided build inputs and outputs. Now, if you've been following along with our Bitcoin fundamentals track, you know we're right in the thick of our capstone project, building and analyzing a full Bitcoin transaction. In our last lesson, decoding transaction components, we learned exactly how to read the blueprints. But today we are rolling up our sleeves. We're transforming from decoders into master builders of raw Bitcoin transactions. So put on your hard hats, let's fire up the machinery and pour some digital concrete. Okay, let's take a quick look at the blueprint for today's build. First up, we're shifting from decoding to building. 2, we'll set our version and counts. 3, we'll assemble the inputs. 4, create the outputs. 5, handle the final hex concatenation. And finally, step 6, we'll verify our fee math so we don't accidentally bankrupt ourselves. Right, so kicking things off with step 1, from decoding to building, it is officially time to put all our theory into practice. You know, in our previous lesson, we were kind of like watchmakers, right? Carefully taking the gears apart just to see how they tick. But now, it's time to gather our raw materials and actually snap them together. Think of it like playing with incredibly technical Lego blocks. But here's the catch with Bitcoin. If we have even a single block left over or misplaced at the very end, the whole network completely rejects our build. No pressure, right? Before we hit the assembly floor, though, we absolutely have to remember our golden rule, little-endian serialization. I know, it sounds like a maddening concept at first, but it's actually a perfectly logical way of reading bytes backward for machine efficiency. Trust me on this, if you don't reverse your byte sequences correctly here, your entire transaction will literally appear backward to the Bitcoin network, and that is a one-way ticket to a rejected transaction. Moving on to step 2, the version and counts. Because every great structure needs to lay a rock-solid foundation. We start off our digital assembly by locking in version 2, that's represented by 4 little-endian bytes, 02 followed by 6 zeros. Right after that, we have to tell the network exactly how many inputs are about to roll down the conveyor belt. We do this using a variant, or variable integer. Since we're dealing with 2 inputs today, our variant is just a simple 02. Just think of it as the header on our digital shipping manifest. All right, step 3, assembling the inputs. Let's start gathering up our raw materials. For this specific build, we're going to use some placeholder UTXOs. That's unspent transaction outputs, if you remember from our Exploring Bitcoin Transactions in UTXO module. So input A brings 500,000 satoshis to the table, and input B brings 300,000. Add those up, and that gives us a grand total of 800,000 satoshis of raw building material to work with. Not a bad stash. Now, we have to serialize each input following 5 exact steps. First up, reverse those transaction ID bytes into little-endian order. Next, append your 4-byte VUT index to pinpoint the exact output. Step 3, and this is absolutely crucial, folks, write your scriptsig length varint. If you get even 1 byte wrong here, the whole structure just collapses. Step 4 is our dummy placeholder signature, and step 5 caps it all off with our sequence number. Repeat that for both inputs, and boom, our formatting is perfectly locked in. Okay, on to step 4, creating the outputs. Now we need to define the final destinations for all those hard-earned satoshis. Let's say we need to send exactly 600,000 satoshis to our primary payment output. Sounds simple enough, right? But here's the thing. We can't just type that number in. Bitcoin doesn't speak decimal. It strictly speaks serialized hexadecimal. So we take our 600,000 satoshis, convert them to hex, and pad them into an 8-byte little-endian format. That brilliantly becomes 40E201 followed by 10 zeros. After that, we add our scriptPubKey. That is essentially the locking script that defines exactly whose digital key can spend this payment later on. Then, we just repeat this exact same process for our change output, which is 190,000 satoshis making its way safely back to us. Which brings us to step 5, the final hex concatenation. Grab your goggles, because it is time for some digital welding. This sequence right here shows the exact chronological order of our digital assembly line. We snap the version and input count into the serialized inputs, we follow that up with our output count, weld on our serialized outputs, and finally, we cap the entire string with a 4-byte lock time. What we get is one continuous, unbroken, beautiful piece of hexadecimal code. And finally, step 6, verification and fee math. Because let's be real, a good engineer never deploys without inspecting the final product. Let's double check our math. We always want to cross-reference our human-readable blueprint with the raw hacks. We need to physically look at those assembled bytes and confirm that the serialized hex exactly matches our intended 500,000 and 300,000 satoshi inputs. And, of course, we need to ensure our outputs properly total up to 790,000 satoshis.
Now, why do we go through all this trouble? Because of the sacred law of Bitcoin engineering, inputs minus outputs equals the fee. You see, there is actually no dedicated fee field in a Bitcoin transaction. It's entirely inferred by the network. So if you happen to forget a zero in your output, the network is just going to assume you meant to leave the rest as a fee. And suddenly, you might accidentally donate your life savings to a very, very happy miner. Yeah, let's definitely avoid that.
Visually, you can see our fee math balances perfectly here. We brought 800,000 satoshis to the table, our payment takes 600,000, our change returns 190,000 back to our own wallet. This proves our inputs comfortably cover our outputs, leaving exactly 10,000 satoshis left over. And that leftover amount, that is exactly what pays the network miners to process this transaction.
So the ultimate test is taking your massive string of concatenated hex and running it backward through a decoder. If the decoder outputs your exact original placeholders, meaning you've got 0 off-by-1 errors in your variants and no reversed byte mistakes, well, congratulations. You just built a structurally valid, fully raw Bitcoin transaction with your own 2 hands. How cool is that? You've built the structure, and syntactically, it is totally flawless. But remember, right now, we are just using dummy placeholders for our signatures. And think about it. If a single misplaced 0 can accidentally donate your savings to a miner, what on earth happens if a malicious actor tries to forge your signature? How do you mathematically prove you actually own the money you're trying to spend? Well, that is exactly what we'll tackle in our next lesson, security and signature analysis. To explore this and to dive into our full Web3 curriculum, head on over to forge.college. Keep experimenting, keep building, and stay curious. I'll see you in the next explainer.